Yeah, I think it has started.
Yeah, recording has started. Okay.
Yeah. Yeah, go on.
Yeah, good afternoon, everyone. Myself, I'm Varun from Booster Dose, and I'm going to present a paper titled DarkGates, a hybrid power gating architecture to mitigate the performance impact of dark silicon in high performance processors. Just to brief about the background. Oh, sorry. Just to brief about the background, the power consumption of a system is actually directly proportional to the frequency of its operation multiplied by and as well as voltage square. And voltage is directly proportional to impedance. That is probably Ohm's law that we have studied, and impedance is inversely proportional to the area of the source. These are a few electrical concepts. Even though I am going to present this paper in CS course, unfortunately this is an electrical paper. Sorry, please bear with me. And a few of the system idle states. Now, what are these idle states? Essentially, every system has every desktop system has states from C0 to C7, while every mobile system has states from C0 to C10. I have mentioned about the four states here for the only reason these four are going to be critical as we go ahead in the paper. But these are the system idle power states that the OS actually takes care of when it wants to power off, power on, power gate certain cores or certain structures inside a system. Now let us understand why do we actually need power gating. There is actually presence of inactive silicon components on chip, and this leads to increased leakage power. And this leakage power is actually due to sub-threshold conduction, which is also commonly termed as static power in our architecture domain. And one of the solutions to reduce the static power consumption is actually to power gate such inactive components. Just to give you a brief overview of what I mean by inactive components or active components, let us assume that this is a quad core system wherein every core has the capability of power gating itself. And secondly, let us assume that for the moment core 2 and core 3 are idle. So in that scenario, normally the total power consumption is nothing but the power consumption from core 0 plus power consumption plus core 1 plus power consumption of core 2 plus power consumption of core 3. But if at all, let us assume that we have this power gating circuits wherein we can actually switch off the supply to these cores. Then in that scenario, actually the total power consumption of the system will be power consumption of core 0 plus power consumption of core 1, since core 2 and core 3 are idle. So this motivates us to look into how to actually power gate and whether what are the issues with power gating and how probably we need to resolve it. So let us directly jump into what are the issues with power gating. The issues with power gating is when you actually power gate a system, you essentially increase its impedance. And when you increase its impedance, the IR drop across that power gating circuit increases. Thus, to compensate for that, we need to actually introduce voltage guard band. Now, when you introduce voltage guard band, the power consumption of the system increases. So when the power consumption of the system increases, the total power budget for that particular system for the active cores essentially reduces. So in that scenario, we need to reduce the frequency of the active cores to facilitate the lower power budget that is available. Now, this leads to system performance degradation. Let us look at how much power gating impacts the impedance of the system.
Hey,
Now,
Varun,
yes, sorry.
previous slide.
Yeah.
Can you maybe provide a high level idea about what is this impedance and how it is related to voltage, like in a CS way, in a CS way?
In a CS way, then probably these formulas will help you probably understand
Well,
when
what
actually
exactly it mean when you say impedance?
actually there you can, for instance, you can assume that that is the resistance. So basically when you have a resistance, right, the destination won't get the entire power that you are actually giving at the input. There will be some drop in the power because
Okay,
there will
okay.
be some voltage drop
And
across that resistance.
higher the area, lower the resistance.
Yes, yes. One of the basic principles that every engineer has learned in his basic electrical is R equal to rho L by A, where A is the cross-sectional area and R is the resistance. and the resistance is inversely proportional to the area.
Okay.
So actually the problem here is when you power gate a system, because of the high impedance, you try and power gate the system in such a way that you try and make sure that the power gating circuit has low impedance. But the problem with low impedance systems is the area increases and our chip area is limited. So beyond a certain limit, we can't reduce the impedance. So then we need to look after the voltage drop across this impedance, and that is why designers introduce this voltage guard band into the picture.
Okay.
And when you introduce the voltage guard band into the picture, unfortunately the power consumption increases. And when the power consumption increases, then the power budget for active cores reduces. And then to run the active cores within the power limit, we need to reduce its frequency. And when you reduce the frequency, then it leads to performance degradation. Sorry, this is too much electrical and very less of CS. I am not particularly sure how to map it
No, no,
to.
no, no. This is perfectly fine.
Yeah.
We should not treat ourselves as experts. Go on.
Okay, thanks. So looking into the system impedance impact due to power gating, the blue line shows the system where there is no power gating, and the red line shows the system where there is power gating. For this, and x-axis is frequency in logarithmic scale, and y-axis is impedance. You can actually look that at every point, the impedance is actually almost double than that when it is not power gating. So essentially meaning that the impedance of the system actually increases by as much as 2x in many scenarios when you power gate the system. So yes, just to put these things in word, power gating increases system's impedance and thus introduces voltage guard band. So what these two do is they actually limit the maximum attainable voltage and the maximum attainable frequency for a particular core. So at times there are certain systems whose performance are constrained by maximum attainable core frequency. For such systems, these systems suffer significantly in performance perspective due to power gating. Now, let us understand if we somehow have a scope of increasing the frequency, how much benefit do we get? Now here in this graph, the x-axis shows the thermal design power. That is nothing but the power budget within which you need to work around or design your system. And the y-axis shows the performance improvement. For this particular graph, the system has been evaluated with 100 millivolt reduction in voltage guard band as compared to the baseline, wherein the baseline system is power gated. Okay, now here this graph shows spec 2006 benchmark applications being simulated, wherein spec FP is floating point applications and spec int is integer applications. Spec underscore base essentially says that application is run in single core, and spec underscore rate is essentially means that it is run in all cores. Now when you look at this, for example, let us look at this 35-watt power budget. Here you can essentially understand that when the voltage guard band has been reduced by 100 millivolt, now the power consumption due to voltage guard band also reduces. So the active power budget that we have now for the system to run increases. Essentially, we can increase the frequency of the system and we can gain performance benefits. But as we move from lower power budget to higher power budget, we can see that the underscored rate, that is the multi-core performance, actually increases because you can increase the frequency of all cores, thereby doing more work and gaining more performance. So this essentially motivates us to target to design our targets. So the paper targets to achieve to reduce the voltage guard band over it.
Varun,
So,
question
yeah.
again. Previous slide.
Hmm?
So this power is for the entire chip.
Yes, absolutely. Entire die.
Yeah. But it doesn't include memory and all, right? This is just the on-chip resources.
On chip. This has nothing to do with the RAMs. Yeah.
And then this is a how many core system?
They have done it in Intel Skylake.
Okay.
Yeah. So now this motivates us to come to the conclusion that we need to target to reduce the voltage guard band overhead due to power gating, and then utilize this reduced guard band voltage to increase the frequency of the cores by maintaining the TDP limit. So now let us see how the proposal DarkGates work. Here comes the proposal. The proposal has three key components. One component is how to bypass the power gate and what do you achieve by bypassing. The second component is improved power management algorithm, and the third component is new package C state for desktop systems. Now let us go into it one by one. When I say that they are doing power gate bypassing, what they are essentially doing is they are reducing the system's impedance. When you don't have power gate circuits, then the system's impedance will reduce. Thus, there is scope to increase the CPU core frequency, thereby improving the system's performance. But then, when you bypass the power gate, as you decrease the system's impedance, the voltage frequency curve of the system improves. Now, to account for this improvement in voltage frequency curve, we need to update the DVFS firmware in the power management unit. And that is being done in the second key component, that is improved power management algorithm, wherein they update the DVFS firmware and they also manage the power budget. Now, why do I say they manage the power budget? The reason is when I am bypassing the power gating, now the idle cores will have some leakage power again. So the effective power budget that is there for the active cores actually reduces. So now I need to manage the power budget a bit intelligently. So they actually update the power budget firmware. Now, sorry that I am just saying they are updating the firmware of DVFS and the power budget, because they have also mentioned the same and they have not actually told us in detail in the paper in regards to what they are doing to update. They are just
This would
saying
be
that
a
there's
driver update, right? The kernel driver, sorry, the power interface.
yeah,
The kernel.
absolutely. Yes, they are doing it. But my point is what algorithm they are using or how they are doing it. That's something that they have not told. They have told that they are updating it in the kernel firmware. That's it. And then coming on to the second point, when we do power gating, when we bypass power gating, the processor's power consumption will increase and it will also increase the heat dissipation. So when the heat dissipation of the processor increases over a period of time, the aging rate increases. So as the aging rate increases, the processor's lifetime reliability reduces. So they need to also improve the processor's lifetime reliability, and they have made up an updated model to improve the lifetime reliability of the processor. Now getting into the third component, that is the new package C state for a desktop. The desktop systems generally support only till package C7 state, whereas the mobile systems support till package C10 state. So when they are bypassing power gating, they observe that in package C7 state, the power consumption is exceeding beyond the TDP limit. So they proposed to support propose to generate support for package C8 state in desktop systems so that the power consumption is within the TDP limit. Now this improves the energy efficiency of the system. So in the nutshell, what they have achieved: bypass power gating, thereby reduce the impedance, thereby reduce the voltage guard band. Thus, now you have an improved power budget. Now you have a scope to increase the frequency of the cores, and thus we can increase or enhance the system's performance. This is in the nutshell that they have achieved using their architecture. Now, how they have tested or implemented their architecture? They have implemented it on Intel Skylake SoC, wherein the SoC has two different systems. That is the mobile system, that is Skylake H, and the desktop system, that is Skylake S. Their proposal is to actually target the desktop systems. So they will implement their proposal on Skylake S and they will use Skylake H as their baseline system. The Skylake die is such as it has both H and S, wherein the ball grid array package is used with power gate enable and the land grid array package is used by power gate
This
bypassing.
is going above my head now. So,
Yeah,
what is it exactly? You are saying both Skylake H and S on a common die.
yes.
Uh,
They are on a common die. So these dies are manufactured in such a way that whenever you want to use this particular chip for laptop systems, right? They fuse Skylake Edge components, and whenever you want to use the die for the desktop systems, they fuse the Skylake S component. This fusing
okay.
part is something related to the fabrication stuff, and since this is a sort of technique that they use for
Why
mirroring
do they do
mirror
that?
design. Huh?
Why do they do that?
See, because in by manufacturing a die, you can actually target two different segments, right? and they have very similar structures, and so mirroring in layouts and all, mirroring and all helps a lot. We have mirrored
No,
circuits or
in terms of microarchitecture, there will be so many differences, right?
No, sir. So basically, these two are basically the only differences between these two will be the power circuits or the power gating circuits or the
That
states
I
which
got it.
with
That
respect
I
to
got
power.
it.
But other microarchitecture structures will be same in both of them.
yeah.
So you can just imagine that it's like i5 Intel core on either laptop or in desktop PC.
Yeah.
So
Oh, so
desktop PC has
microarchitecture is same.
Yeah, the power management system, the firmwares that will decide, means certain cores will allow frequency boosting, certain cores will not allow. So these things will change, but otherwise
No,
the
no.
microarchitecture structure.
My question is pretty simple. For example, if I'm using a desktop, my cache size will be in tens of MBs. But if I'm using a mobile, then my cache size will be in the lower side of MBs, right?
Okay, so sorry to say this, mobile essentially means the systems that are battery dependent, and they are meaning laptops here. They are not actually meaning mobile.
Ah, okay.
Let me be very clear. Mobile systems are actually systems which can run on batteries.
Okay. Got it. Yeah. Then it's more or less the same. Yes,
Yeah.
makes sense.
So I just use this figure to just give an overview, even though most of things even went over my head. So, sorry. So, as far as hardware cost is concerned, depending upon the silicon fuse value, the dark gates operates in two modes. That is, one is the bypass mode, that is bypass power gating and increase the core frequency, or another is normal mode, wherein you power gate the idle cores to reduce the leakage power. Just to go back, I just wanted to say that fuse value essentially means whether I am using this configuration or S configuration. If it is H configuration, it is normal mode. If it is S configuration, it is bypass mode. And the additional firmware code actually they state that it requires 0.3 kb area, which is very much less than 0.004% Intel Skylake's die area. Then getting into the hardware cost for package C8, since package C8 is already available for the mobile systems and the firmware is already available, we actually need not have any additional cost for supporting package C8 for desktop systems. It's just a very slight variation in the firmware. So now getting into the evaluation methodology, they implement this on Intel Skylake die. They use Intel's in-target probe to configure the processor, and the National Instruments data
What is it
acquisition.
exactly? This ITP?
This is a particular connection to the JTAG of the chip, that they said that the probe is connected to the JTAG, and then they are able to configure they are actually able to program the firmware.
Okay.
I did not go into the details of that because it would have been too much.
But this is this is done or accessed through kernel, or even user can do that.
No, this is access through kernel.
Kernel only. Okay.
Yeah.
So it will be highest privilege level.
Yes, absolutely. And the National Instruments data acquisition card is being used for power measurements. This is a standard instrument that is being used, and so that's quite common. And DarkGates is actually evaluated with three class of workloads. One is the Spec 2006 workloads, then this 3D mark benchmarks that are graphic workloads, and some energy efficiency workloads, which I will talk about later. So just getting into the evaluation part, you can see that on an average 4.6% performance improvement is achieved at 91 watt TDP limit by DarkGates over the baseline, wherein there is bypassing and we support only C7 states. And
This
then
is on a real system, right?
real system Intel Skylake, yes.
Yeah, real
So
system
they have time
4.6.
and again mentioned the sentence that their results are very significant because they have done everything in real systems. Yeah. So just to mention about the few benchmarks, these two benchmarks as highlighted, they are heavily constrained by the CPU core frequency. Thus, you can actually observe highest performance benefits for those systems as you have a scope of increasing core frequency. Similarly, for benchmarks BVS and MLC, you can say since they are heavily constrained by the main memory accesses, even though increasing frequency hardly has any benefits on the performance. So you have both sides of the story. Then going into just sensitivity analysis of TDP limit, underscored base essentially again means single core, and underscored rate essentially means all core are being used. Here you can observe that as the TDP limit increases, the base performance improvement actually reduces because the baseline performance also improves as TDP limit is increased. But whereas when you look at the rate performance improvement, it actually, the light blue bar actually shows more improvement as the TDP limit is improved, because now you have more scope to increase the frequency of all cores. Now getting into the graphic workloads, that is that the graphic applications that they have run on the Skylake. Here you need to understand that there is a graphic card also in this Skylake processor. So one of the assumptions that they say is only one core is active from the CPU cores, and then the graphic core is kept active. The other cores are idle. So in that scenario, they say that for 35-watt TDP limit, there is performance degradation of approximately 2%, whereas for 45-watt it is very insignificant, and beyond 45 watts you actually have no performance degradation. So DarkGates actually works for higher TDPs is one of the conclusions that we can take from here. Now the third, energy efficiency workloads. Energy Star and RMT are very special workloads. Just to say a few things about Energy Star is such workloads which works for 1% of its total execution time. It stays in C0 state, which I earlier mentioned as a state wherein the entire system is active. And more than 98% of the time, it is either in C7 state or C10 state, wherein hardly any system is active, or only just one particular core is active and others are power gated or something like that. So in that scenario,
can you comment on these workloads? What do they do exactly?
Energy Star, I can maybe just give me a moment.
No, these are benchmarks written keeping like what particular attribute in mind.
This Energy Star workload is kept in the mind to check how much benefits we achieve out of power getting. Means Energy Star is such a
But I
workload
got it.
wherein
But what exactly is this RMT and Energy Star?
okay, RMT. Sorry, the full form of RMT is actually Intel Ready Mode technology. Basically, these are such workloads which have long idle phases where system enters into the idle states.
Okay. Got it. Okay.
Yeah.
So these are
So,
not like spec. That's why they are evaluated differently.
yes, absolutely. Yeah. So looking at these, there is something, this horizontal line I have tried to highlight here. The reason I have tried to highlight this horizontal line is your energy reduction has to be bare minimum up to this limit. Otherwise, you wouldn't come under the TDP limit. And when you look at the Energy Star for DarkGates plus C8 support, you see that the performance, the power reduction is on an average 33%, whereas for non-dark gate essentially means where there is power gating and where we only support C7 state, we see that the power reduction is 37%. But now you can see that the difference here is only 4%. So what I mean to say is in this 4%, we are almost reaching up to the 4% limit by not power getting. So this is one of the benefits of dark gates. So then let me conclude fast. Actually, DarkGates enables processor firmware optimization and customization. It helps us overcome the limitations posed by power gating for desktop segment systems, and it's an effective hybrid power gating approach to meet the power and performance demands. Now, to just mention a few drawbacks about DarkGates, it actually reduces the reliability of the processor, on which we need to work on. Maybe if we can come up with a better cooling system, we can actually improve the reliability. Second thing, it degrades the performance.
Can you quantify reliability like?
No, it's like once the power consumption of the system increases, and so you tend to increase the number of hotspots on the chip. So
the
when the number
lifetime
of
goes down.
huh?
So the lifetime goes down, is it?
Yeah, because then the aging increases. When the aging speed ends, then the lifetime goes down.
Okay.
Yeah. So the second point is it degrades the performance of the power limited processors, wherein hardly few cores are active. Because when most of the cores are idle, then huge number of cores actually consume leakage power when you are not power getting. So this degrades the performance of the power limited scenarios. And third, this requires separate designs for target segments. Now, suppose I am moving from Skylake to maybe let us assume Broadwell, or maybe let us assume some different architectures. So in these architectures now I need to study the designs and accordingly modify the firmware for each design. So this design can't be used for every design, every target segments. Thank you.
So I have a question on their proposal.
Yes.
So how do they tackle power getting at the shared resources like on-chip interconnect or last level cache?
No. The point that I'm trying to drive here is the Skylake die supports two kind of processors, right? So the silicon fuse value essentially says, are you going into Skylake
Got
H or
it, got it,
Skylake S?
got it.
Yeah.
That I got it. I am asking in terms of technicalities. So when you say that the power getting is actually the older way of, or the current way of doing power getting is actually not good.
Yeah.
So in terms of implementation, you are talking about power getting for a core, right? Your processor pipeline and other
Yes.
things,
Yes.
and the
Absolutely.
private resources.
Yes.
But what about shared resources?
Shared resources. I'm not particularly well aware of whether the today's system power get portion of shared resources or not.
Yeah,
I'm not.
they do. They do.
Okay, no, because they have not come up with some middle path. They are just saying that if you are using Skylake H, you will use all the power gate circuits. If you are using Skylake S, you won't use any power gate circuits.
Got it. Got it. Got it. No, the reason I'm asking is the example that you use to motivate that I have a 4 core system and let's say 2 cores are idle.
Yeah.
Then it's just unnecessarily you are wasting power, right?
Yes,
But
absolutely.
but what about the shared resources that are shared by all the cores?
Uh, yeah, the shared caches and everything. Yeah. There will be power consumption, but since these cores are not going to access, right? So at least the contribution of these cores towards the power
Yeah, that I
consumption
got
and the
it.
shared resources will reduce.
Yeah, that I got it. But I'm asking in terms of implementation, like how exactly they have differentiated.
No,
You know.
they haven't. They
Yeah.
haven't.
Yeah. Okay. 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 Yeah, I'm good. Others, any questions? Or this is a bouncer completely.
Complete electrical course, maybe.
It's not that electrical, to be honest. Maybe 2 3 terms. That's all. It's
No,
hardcore
there's
systems.
another thing to answer your question, Viswa. There is a table in the paper. Actually, I did not get into detail. I just used these four states to explain. There are some middle states from C0 to C7. That is C1, C2, C3. Every number has its own state. So at certain stages, like for example in C6, C7 state, right? What he is doing is here LLC may be flushed and turned off. DRAM is in self-refresh mode. So basically, these states take care of that, and OS actually
Okay.
handles these stuffs.
Okay. 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 Got it.
Yeah.
Okay. It seems that there are no queries. Okay. So we can stop the recording. Devasis or Virendra, whoever is recording it. I guess it's done.